first. All right, now I will share my screen. Let's put it up here. Participants and the chat box. All right. So, in this second part of today's lecture, I'm going to finish talking about this plane sweep algorithm in which we draw diagonals to get rid of split and merge vertices in a polygon. And at the end, we will have ourselves a Y monotone polygon or multiple Y monotone polygons, as each diagonal is going to divide the polygon into two pieces. And the implementation details of this, for example, what kind of data structure we need to represent these polygons, either as an ordered list of vertices, or you may even have a doubly connected edge list to represent the polygon too, with all the nice next pointers for each edge. You can actually have that. But I'm not going to focus on those implementation details. I'm going to focus on the algorithm in which we draw these diagonals for getting rid of split and merge vertices. For that, this page from the book is extremely critical in understanding how we're going to do this. Okay. First of all, this plane sweep algorithm is very easy. In the sense that the event queue is static. Only the vertices are going to be in the event queue. So we just need an ordered list of our vertices with respect to their y coordinates in decreasing order. Okay, and the vertices from left or right chain, they are stored arbitrarily. So our event queue is static. It just contains the vertices of the polygon in decreasing order. So what you can do is you can just put the vertices in an array and sort them in n log n time, and that becomes your event queue. And in O1 time, you can get the next event from that array. The status structure is a little bit interesting. I'm going to come to that later, but because the status structure is going to contain data that we need to draw these diagonals. It's very critical in that regard, and it's going to store edges. The sweep line status structure is going to store edges that intersect the sweep line, but not all of the edges. We will only be needing edges in which the polygon lies to their right. For example, this EJ is going to be in the status structure, but EK will not be in the status structure. We will not store EK in the status structure. And this edge here, it will be in the status structure because the polygon lies to its right, but this one will not be in the status structure because the polygon is not to its, the polygon's interior is not to its right. So we will only need edges in which, if you look at their right, immediate right, the inside of the polygon is there. And the reason we do that, we have these edges, is actually we will be using what we call this helper vertices of these edges will be the main data to draw these diagonals. So for that, it's extremely, to understand what an helper of an edge is, we need to understand these paragraphs very carefully. So the way we are going to draw these diagonals, again, we need to find a way to figure out to draw safe diagonals. For example, from a split vertex. Look at the split vertex. We are going to draw a diagonal to some vertex above. Which vertex is a good candidate? It should be a vertex that is not very far away. For example, if I try to draw a diagonal to an arbitrary vertex, that may not be a valid diagonal. So I need to find a vertex above Vi when I come to this event point Vi, and I can know that whether it's a split or a merge vertex. And by the way, the algorithm, at the start of the algorithm, I may go over all of the vertices in linear time, one by one, and for each vertex, determining its category, whether it's split vertex, merge vertex, or regular vertex, start vertex, end vertex. This can be done in all one time for every vertex. So in total, in linear time, I will be able to label each vertex with its category. So when I come to this vertex vi, when I handle this event, so my event points are vertices, don't forget that. So I'm sweeping the line from top to bottom, and when I come to an event point like this vertex, I'm going to handle it. And handling the event point, the vertices will be done based on with respect to their categories. So when I'm handling the split vertex, vi is a split vertex by definition. So what I need to do is I need to draw a diagonal, so I get rid of this split vertex. And as I said, the way to draw a good diagonal is to draw to some vertex which is close enough, which it's guaranteed to be a valid diagonal. And these helper vertices are such vertices, which a helper of an edge is defined in such a way that if we draw a horizontal line to the edge, there is nothing else. The line is completely inside the polygon, and the helper is the one that is at bottommost, with the smallest y coordinate of such possible vertices that exist. For example, do I have multiple? Yeah, look at this one. At this point, if you look at this edge EJ again, okay, if you look at this edge EJ, so it's going to start like this. Actually, I just want to again copy this to show you, to tell you the definition of helper vertices. I'm going to copy this one to GIMP. All right, get a new one. All right, and let me enlarge this a little bit more. All right, and move it here. Okay. Okay, now let's look at this edge. Oops. Yeah, let's look at this edge EJ. By the way we label the edges are going to be like this. If this is a vertex, if we start vertices here, for example, V1, V2, V3 in counterclockwise order like this, V4, sorry, this is going to be V4, V5. The edges are labeled which connect, for example, this is going to be E1. Okay, the edge is going to connect V1 and V2. EI is going to connect VI and VI plus 1. Let me check that again. All right, here. This is how edges should be defined. It must be, yeah, right here. So it's defined here. An edge is connecting, it's labeled in such a way that it connects vertex I and vertex I plus 1. And the last edge connects vertex n to vertex 1. All right, so en will be equal to actually this. All right, so if we have this definition, if this is V1, this is V2. Okay, so this is V2, this becomes E1. So for example, V5, V6, this is actually E5. Okay, now this is how the edges are labeled to understand what happens in the algorithm, because we will be referring to edges in the algorithm to indicate what we are storing, what we are, how we are setting their helper edge and things like that. Now, at the time when the sweep line comes to this vertex V5, edge EJ or E5 is going to be inserted into the study structure because the polygon lies to its right. Okay, when we insert EJ or E5 to the study structure, we are going to set its helper vertex to be this top point, or in other words, let's call helper. Okay, helper E5. Helper E5 is equal to V5 at this point, at this sweep line. Let's call it L1. When we come to this event point, when we come to V3, let's call the sweep line L2. Okay, so at L1, we have the helper set to V5. When we come to L2, we are going to update the helper, let me just call it H, helper of E5 is now going to be V3. Why? Because V3 becomes the bottommost vertex that is closest to this edge EJ. In other words, if I draw a line from EJ, a horizontal line from EJ to here, V3 is the bottommost such vertex. Okay. Now, when I come to the sweep line, which is this dashed line, when we come to this L3, the helper of E5 is going to be this time VI. Actually, it's V2, right? In our figure, VI is equal to V2. It's going to be V2. So we update whenever we come to these event points, these vertices, the helper of an edge is always a vertex, and it's the vertex which is bottommost and closest vertex to its right. You can consider it as this. Look at this edge towards its right. It's the lowest vertex that is closer to VI. There may be other vertices here, but VI is the closest vertex. Now, what happens is that these helper vertices help us. A helper of an edge is going to help us. It's right here. When I come to this VI, what I will do is I will locate the immediate left edge EJ to its left. If it's a split vertex, I will look for EJ on the study structure. Because I know it's X coordinate, I can make a query in the study structure, which is the balanced binary search tree. I will make a query saying that get me the edge, which is immediately to the left of the X coordinate of this VI, and it will give me EJ. And in the study structure, for every edge that is in this study structure, their helper field, it may be a field of this data structure, it may be some additional data that you're storing with the edge. We will store these helpers of these edges. And here, the helper of this edge at this point is this vertex, because at this sweep line here, the lowest, the bottommost vertex that is closer to EJ is this vertex. And what we will do is we will draw a diagonal from VI to the helper of EJ safely. It will always be a valid diagonal. Helper vertices main purpose will be to mark a safe diagonal for anybody that is potentially appearing to the right of EJ. And at this point, you may also see that VI below this point, below this sweep line, VI itself is going to be the helper of EJ, right? If you look at this, EJ now, below this dashed line, VI becomes the bottommost vertex to the right of EJ. So VI is going to also update EJ's helper. Okay, that's how we are going to get rid of split vertices. When we come to a split vertex, we are going to draw a diagonal to the helper vertex of EJ, the edge which is immediately to the left of the split vertex. Now, what about merge vertices, which are more difficult to handle, but we'll see that they're not so difficult. By the way, if you read this paragraph, there is also a formal definition of helper, the last second from last sentence of this paragraph. So helper of an edge is defined as the lowest vertex above the sweep line such that the horizontal segment connecting the vertex to EJ lies inside P. So this is the same as what I already told actually. Note that helper EJ can be the upper endpoint of EJ itself. The point we add EJ, so it's this one, sorry. The point where we add EJ to the study structure, its upper endpoint is the vertex that satisfies this definition. So V5 can be the helper of E5. But when we encounter V3, we update its helper. When we encounter V2, we update its helper. So the updates are going to be the helpers are going to be updated, and also the final thing that we need to discuss is how are we going to handle merge vertices, like merge vertices. Okay, so here this is also this is a merge vertex. Okay, when we have a merge vertex, what happens is that merge vertices, we cannot draw diagonals to vertices that we haven't seen before. So when we come to this event point vi, which we know is a merge vertex, we cannot get rid of this its merge category at that point, because we have to draw a diagonal to some vertex that is below, right? And we don't know, we haven't yet encountered any vertices that are below. So it's against the rules of plane sweep algorithm. We don't know anything below the sweep line. And therefore, what we do is we do not get rid of VI's merge category at this point, but we will get rid of it when these conditions happen. For example, at some point below VI, okay, at this point, if you see, when we come to event point VI, what does it do? What does it update? It updates EJ helper, right? EJ's helper vertex becomes VI when we come to event point VI. So VI says that I'm your new helper. Okay, VI is the helper of EJ. Now, when we come to VM, VM now says, now I'm going to be the new helper of EJ. Now, when we have an update on the helper of an edge, we check whether the previous helper was a merge vertex or not. If it is, we draw a diagonal. So we get rid of this VI actually. We get rid of VI's merge category when VM updates itself to be the helper of EJ. What if such a vertex does not exist? What if EJ ends? What if VM does not exist and EJ, we come to the end of EJ and it's deleted from the study structure forever? What do we do then? At that event point, when EJ, which is a regular vertex by the way, look at this, EJ is a regular vertex, and at that point we are going to delete EJ, and this endpoint, this one is a regular vertex, which is EJ plus VJ plus 1. Okay, if this edge is called EJ, and this vertex that my mouse pointer is now on top of should be VJ plus 1, and this is VJ. Now, the vertex VJ plus 1 at this point, it's an event point, and it's at that point also is saying, oh, okay, I'm a regular vertex, but I need to update helpers of EJ to be me because I'm the lowest vertex that below the sweep line. And at this point, again, we ask ourselves whether even if VM did not exist, we will ask ourselves whether the previous helper was a merge vertex, and we will draw a diagonal from this to that. All right. Sometimes we may need to draw a diagonal from the end of an edge to the merge vertex to get rid of its merge classification. Okay. Now the idea is merge vertices are going to be handled below the sweep line due to other event points below them, not due to the merge vertex themselves. So this, with these observations, we can now take a look at the final algorithm in which all of these cases are handled with very short pseudocodes. We are going to have 5 different functions for 5 different category of vertices, and we can actually go over this running example. Where is the running example? Yeah, this one. If you look at this running example in the book, you can actually try all these functions on this and see how the algorithm proceeds. We can start a sweep line from V5 and following the events like this: V5, V3, V4, V6, 7, 1, 9, 2. So they're going to be processed in order of their y coordinates. Okay, and the main algorithm is just not different than any other plane sweep algorithm. We just construct a priority queue for our events. This is the event queue step 1 construct the event queue, and initialize an empty status structure. So this T is our status structure. While the event queue is not empty, remove the next event from the queue and handle that event with respect to its type, its category. Call the appropriate procedure to handle that vertex depending on its type. So here are the functions, the 5 separate functions in increasing difficulty, we may say. Handling a start vertex is really easy. You don't need to do anything. So when you have a start vertex, actually, I'm going to go over this running example. Look at this start vertex, like V5. When we come to V5, what should we do? We should insert into the status structure only E5. E4 is not added to the status structure because if we have a start vertex, we know that since it's a counterclockwise traversal of the polygon, we know that E5, the polygon lies to the right of E5, so E5 is added to the status structure and E4 is not added to the status structure. Okay, the status structure, I repeat, contains only edges in which the polygon's interior lies to their right. Okay, so what we do is when we come to a start vertex, we just insert this. When we come to this V5, E5 is inserted into the status structure, and E5's helper is set to be V5 at this point. So the upper endpoint becomes its helper. Okay, we need to, all of the edges that are in the status structure, they have to have their helper set to some value. They cannot be undefined. And at an end vertex, we do this when we are handling a vertex Vi. Look at this V11. When we are handling an end vertex like V11, the one that is actually the edge that is associated with V11 and that is in the status structure is E10. Okay, so in other words, if we are handling Vi, EI minus 1 is the one in the status structure. So it should be deleted now from the status structure when we are handling an end vertex, and this edge EI minus 1 should be deleted from the status structure. But before we delete it, we ask ourselves, was the helper of I minus 1 a merge vertex? If it's a merge vertex, then we draw a diagonal from V11 to that merge vertex. Okay, so here's that. If the helper of EI minus 1 is a merge vertex, then insert the diagonal connecting VI to helper of EI minus 1 in the doubly connected edge list. I mean, if you maintain these diagonals and everything in the doubly connected edge list, this is how where you will put these data. All right. Now, these diagonals, it's not very difficult to prove. For example, if V11 is the new helper vertex, is it always safe to draw a diagonal to the previous helper? It should be so, right? I mean, because if there was any other vertex that is in between, that should be that violates the definition of helper. It should be a valid helper because the entire interior of the polygon should be in one connected region for that helper. There should be no vertices below it, which violates this connected property of to the right of that edge. So whatever helper of current helper of that edge is, the new helper. So in other words, this is a statement that we can prove easily. When we update the helper of an edge, it's always safe to draw a diagonal from the new helper to the old helper. Okay, so this way we can get rid of it. And we draw this diagonal only if it's a merge vertex. We don't want to draw unnecessary diagonals. We want to just draw minimal number of diagonals to get rid of Y-monotone breaking instances. You only want to get rid of merge vertices and split vertices. That's why if it's a merge vertex, we draw the diagonal and we delete EI minus 1 from the status structure. So these are the two functions which are very simple. And they are handled like this. The remaining three functions are like this. For a split vertex, if we come to a split vertex, for example, E14 here is a split vertex. E14 is a split vertex, sorry, V14. V14 is a split vertex. What we do is we first search in the study structure to find the edge immediately to the left of V14. Since it's a balanced binary search tree, we perform an upper bound query with this X probably, and which will give us this E9. E9 is the edge immediately to the left of V14. And we insert the diagonal connecting V14 to the helper of E9, which is V8 in this case. So we insert this diagonal. So we always draw a diagonal to get rid of this split vertex. Now this V14 also becomes the new helper of E9. The helper of E9 is now updated to be V14. And insert, since this is a split vertex, as you can see, two new edges start intersecting the sweep line, and only one of them is going to be added, because only one of them is going to have the interior of the polygon to its right, and that's E14 in this case. So we insert EI, which has the same index as V14. We insert EI into the study structure and set helper of EI to be V14. So whenever we insert a new edge into the study structure, its upper endpoint is the initial helper of that edge. So this is how split vertex is handled. When we come to a merge vertex like V8, here's a merge vertex. Here's how we handle it. If it's the helper of its, so here, since it's a merge vertex, it means that one of the edges is ending. E7 should be deleted. So that's step 3, as you can see. Step 3 of the algorithm is delete E7 or EI-1 from the study structure. So before we delete it, we ask this question: was its helper, was its previous helper, like this V2 here, is a merge vertex? And indeed, that's the case actually. V2 is another merge vertex. V8 is a merge vertex. V2 is also a merge vertex. So E7's previous helper was a merge vertex. Then we need to draw a diagonal so that the V2's merge type category is deleted. Okay, V2 becomes a regular vertex. Now, one thing that is interesting here is that both of them are merge vertices, and we draw a diagonal here, but we draw this diagonal only to get rid of the mergeness of V2. Okay, V8 at this point, it's still a merge vertex. If you look at it, I mean, both of its neighbors are above. V2 and V7, they're both above, because we're drawing, at this point, we have drawn a diagonal somewhere to the top. And therefore, V8, this diagonal, drawing this diagonal, does not get rid of the merge category of V8. It was to get rid of the merge category of this, its helper. And we search for, in T, to find the edge directly to the left of VI. So we look at this one, because we need to update the helper of this. So when we come to V8, we search for this edge E9. Again, if its previous helper was a merge vertex, again we draw a diagonal to that. So we may need to draw two diagonals, as you can see in this handling of the merge vertex. And both of these diagonals, both of them, are to get rid of some merge vertices that are some vertex other than VI itself. VI still remains a merge vertex after drawing of these diagonals. Okay, VI's merge category will be deleted when we come to another event point that is below it. And now this EJ's new helper becomes VI. And that's how we handle the merge vertices. And the final thing is regular vertex. And there are two cases where a regular vertex appears in our plane sweep. One of them, it appears on the left chain like this. Actually, in this example, there are no regular chains on the right chain. In other words, we may have a regular vertex in which the polygon lies to its right, or we may have a regular vertex in which the polygon lies to its left. So in both cases, we do similar things, but we insert different edges at each time. So if the interior of the polygon lies to the right of VI, that's the case for V7 and V10. Both V7 and V10 are such regular vertices in which the polygon is towards their right. And we look at their helper vertices that are associated incident to this vertex, E9, and at this point E6 is going to be deleted from the study structure. So we check whether their previous helper was a merge vertex. If that's the case, we insert the diagonal. And then, since it's a regular vertex, at a regular vertex, the edge at the top is deleted, but the edge at the bottom has to be inserted into the study structure with its helper set its to upper point, which is VI. So this is what we do here. For a regular vertex that appears on the right chain, in which the polygon is immediately to the left of them, what we do is we just, since EJ is going to be deleted now, we check its helper vertex. This is the place where we update its helper vertex. And before we update, we check whether it was a merge vertex. If it was, we insert the diagonal. And that's it. So after this point, we have ourselves a Y monotone polygon, or actually a number of Y monotone polygons, which can be then triangulated easily in linear time using the next algorithm that I will describe. Okay, so, and the algorithm takes each of these, searching, for example, inserting something into the study structure, searching in the study structure, or deleting something from the study structure. When we have a balanced binary tree, each of these operations take log n time. And since if we don't have any loops here, there are multiple log n operations. So it's O log n in general. So each of these handle event functions is O log n. And since I have n event points in my plane sweep, in total the algorithm takes n log n time. And the storage it uses is just linear. We don't store anything other than the edges, and the number of edges we can have is linear, O(n) at most. So this leaves us with the final theorem, or lemma, theorem. A simple polygon with n vertices can be partitioned into Y monotone polygon pieces in O(n) log n time with an algorithm that uses O(n) storage. So that concludes the second part of this chapter, second section, in which we just have seen a plane sweep algorithm to convert any simple polygon into Y monotone pieces. And after the last part, I'm just going to show you a very simple algorithm. It's not very simple, but its implementation may not be that difficult. It's a linear time algorithm, and it uses a stack data structure. In that sense, it's very similar to the convexal algorithm, in which we are going to just maintain a stack and process vertices on top of the stack, and when we delete them, they will be deleted forever. So here is an example. Actually, this is the top of an example Y monotone polygon. On the slides, there's a better Y monotone polygon. Look at this Y monotone polygon. This is a Y monotone polygon. One property of Y monotone polygons is that they have two chains, left chain and right chain, and they have one top vertex like this. And as you can see, the left chain contains vertices which are strictly, they're decreasing, or they have the same Y coordinate, but they're all decreasing. And there's a bottom vertex. Vertex 1 is the bottom vertex, and we have a left chain and we have a right chain. And what we do is we merge these left and right chains into a single Y sorted vertex list, just like the plane sweep algorithm. And we are going to process them starting with 17, then go to 16, 15, 14, 13, like this. Okay, so sometimes we jump from left chain to right chain, from right to left. And each time while we're doing this, whenever we can draw some diagonals to the vertices at the top, we do that. Otherwise, we just continue processing the next one. So the algorithms is like this. So actually, let me show you the pseudocode. This is the algorithm to triangulate a Y monotone polygon. So the first, we have a Y sorted order of vertices. They're ordered. And we have a stack. We use this stack data structure to maintain a certain number of vertices at the top, which are not diagonalized yet. Initially, we put the first two vertices to the stack, and for the remaining, this for loop, it just goes over them once in linear time, starting with the third vertex, goes all the way to the vertex before the end vertex. What we do is, if the current vertex that we process is uj, and the top of the stack are on two different chains. By the way, at any moment, the top of the stack is going to contain vertices that are all from the same chain, except maybe the one in the bottom, but the other ones are all from the same chain. So if the next vertex that we process and the top of the stack are on different chains, we get ourselves a very easy situation. We can draw diagonals from this uj to all of the vertices on the stack. So what we do is we pop all of the vertices from the stack and at the diagonal between uj and each popped vertex, except the last one. Because the one at the stack bottom at this point already is one of the endpoints of the edge that has uj, because uj and the bottom of the stack are on the same chain. They are actually sharing, they are two endpoints of the same chain. So it's like this. Let me show you on the book. It's actually better. So if you look at this, this is uj. These are the ones that are on the stack. Okay, stack. This is the stack top. If stack top is on a different chain than this vj, these are all the others that are already on the stack. And if you look at the bottom of the stack, which is this vertex, when we just before processing vj, the stack contains these vertices from top to bottom. This is top, one before top, the two vertices before top. This is the bottom of the stack. As you can see, the bottom of the stack and the current vertex that is on the different chain are actually two endpoints of edge E. Therefore, there is no need to draw a diagonal from vj to the bottom of the stack. So what we do is we draw diagonals to all the other vertices on the other side. So because of the Y monotonicity, it will be safe to draw diagonals to the other chain. Okay, because the Y monotonicity, the first step of the algorithm, ensures that this is something safe we can do. Now, if they're on the same chain though, the situation is different, in which we can draw some diagonals, but some diagonals may not be possible. Actually, it's also here, right here. If they are, for example, if vj is the same chain, it's the same situation. This is the top of the stack, second from the top of the stack, and this is the bottom of the stack. Now, look at this new vj. It's on the same chain as the other ones. But we can draw a diagonal. If it's in the same chain, first of all, it means that there's an edge from vj to the top of the stack. Okay, if they're on the same chain, this edge exists. Now, we can draw a diagonal maybe to this one, to this one, to this one, but we cannot draw a diagonal to the bottom of the stack. Or at some point, we may not draw a diagonal to any one of, even to this one. For example, vj to the second from the top of the stack, we cannot draw a diagonal. So what we will do is, we will start, but the good thing is that the ones that we can draw diagonal are in order at the top of the stack, starting with the topmost one. We already have an edge between them. But checking one by one the edges in order from the top of the stack, if we can draw a valid diagonal to that one, we draw. For example, here we can draw a valid diagonal, we pop it, and we just get rid of it. This diagonal is drawn, and we have a triangle for ourselves. We draw this diagonal, we pop it, and we get rid of this. Now we draw a diagonal to this one, but we cannot draw a diagonal to the other one. Therefore, what we do is we need to push this again to the stack if we cannot draw a diagonal to the next one. So it's described in the pseudocode like this. If so, if they're on different sides, we draw diagonals to all of them, and the previous one and this one is pushed back onto the stack because that at any time the top of the stack should contain at least two vertices. So it's like this. If you look at this picture again, where they're from the different sides. Okay, so when we draw all these diagonals, the part that is not diagonalized yet is below this part, and this vertex and this vertex here should be they should be the vertices now to draw diagonal potentially from other vertices below. So this becomes the bottom of the stack. This becomes the top of the stack. All right, these two, they become the only members of the stack after this point, after we execute this part of the if statement. If they are on different sides though, if uj and the top of the s are on different side, first of all we pop s because we are not going to draw a diagonal to that because there's already an edge between uj and s. We pop the other vertices from S while they're visible from uj. This means that if we can draw a diagonal from uj to a vertex on the stack, we add a diagonal between uj and then each pop vertex. At the point where we can't draw a diagonal, we push the last pop vertex back onto S, and we push also uj onto S, and that's it. So after we come to the last vertex, un, we add diagonals from the last vertex to any remaining vertices on the stack. If there are any remaining vertices on the stack, we draw diagonals from un to those, and this concludes the algorithm. At the end, our Y monotone polygon will be nicely triangulated. Okay, and these show the figures on the book show the cases of these two, of this if statement, where we may have Vj on the same side as the top of the stack or on different sides. And the same algorithm is described in the book with this simple pseudocode. And the algorithm takes linear time. As you can see in this for loop, we just popping things onto the stack takes one time each. And this is a for loop that goes over the vertices one by one. And hence we get ourselves an ON algorithm. And the final theorem of this chapter states that a strictly Y monotone polygon with n vertices can be triangulated in linear time. And that's it. This is we conclude the book with this chapter with this. And the algorithm actually could also be used to triangulate non-simple polygons if they have holes in them. This algorithm, with little modification, it may still work for this polygon. So the last paragraph explains that, but I'm going to skip that part. So this is where I want to conclude this chapter. We have seen two algorithms. One, to make an arbitrary simple polygon converted into Y monotone pieces. And given a Y monotone polygon, we have seen an algorithm to triangulate it by drawing these diagonals. All right, and this one solves the art gallery problem because if we have a way to triangulate a simple polygon, then we use this tree coloring idea by traversing the dual tree of the triangulation. We color the vertices of each triangle with one of those three colors, black, or red, green, blue, if you want them colored. Okay, and each triangle vertices will be one of those three colors, red, green, blue, and you just pick the smallest class and put your cameras at those vertices to guard your polygon in floor of n over 3 places. Okay, so that's it for this week. This concludes our week 4. Yeah, I will not have a synchronous lecture for section 1 tomorrow. So I will put these recorded videos on YouTube. and Section 1 students will be able to watch these videos. If you have any questions about any of these algorithms, feel free to send an email to me. And also, the homework, the first written assignment is posted on OtiClass. Don't forget to submit it before the deadline. It contains 3 questions, written questions that you will have to solve. You should be able to do it in 1 or 2 hours, or although you have more than 10 days to work on it. So you should be able to solve it in a couple of hours. All right. But again, let me know if you have any questions. Do you have any questions from this chapter? No? Okay. So thank you, everyone. Have a good night. I will see all of you next week, and we will talk about chapter 5, which is, chapter 4, which is I think linear programming. Yeah. We are going to see how to, this is the place where we are going to see a nice linear time algorithm to solve 2-dimensional linear programs. The motivating problem seems to be 3-dimensional, but we will be solving another 2-dimensional problem, geometric problem in chapter 4. All right, take care, everyone. See you all next week. Have a good evening. Bye-bye.